Okay, so in this section, we're going to be going over rational functions. Now, first of all, what is a rational function? So a rational function is going to have the form where we have f of x is equal to p of x over q of x. Right? So p of x and q of x, both of these are polynomials. So the last couple sections we spent talking about polynomials, right, finding the zeros of polynomials, and all those tools are going to come in handy when we are working with rational functions. Things that we're going to want to do are mainly graph them, but also develop a language, a vocabulary to discuss what is called local behavior. Right. So, and we'll get into what I mean by that as we move forward in this section here. But before, right, p of x, right, some polynomial degree n, right, had this form here. Oops, a1 x1 plus a0, right, the constant term. Right, just the general form of the polynomial of degree n. Right, now what we knew about this is that the domain was all reals, and the range depended on what the degree was, right? If it was what the degree and the coefficient was, right? Kind of those two things. If it was even degree with a positive leading coefficient, then it went from up to infinity and then down to depending on what the vertex was, right? Or excuse me, right? Not necessarily a parabola, just depending on how low that graph went. And then we need to know some other piece of information there to determine that, right? But for sure, the domain was from negative infinity to positive infinity. Now, unfortunately, based off of the formulation here, we cannot make that assumption here. And in fact, most of the time, I think actually all the time, right, it will not be all real numbers, right? And the reason for that is we're dividing by some function of x, right? And then one thing about division, right, is that we cannot divide by zero, right? Division by zero is undefined. Excuse me. All right, so as we kind of work through these, right, and we're asked to find domain, we want to pay special attention to the denominator of my rational function. All right, that's going to be the key to kind of tell me, all right, am I dealing with what values must be excluded from the domain? All right, the numerator can be zero. That's fine. 0 divided by 8 is 0, for example. But 8 over 0, that's an undefined quantity. Okay, so in general, write some examples. Of rational functions. We could have like f of x equals to 1 over x, 1 over x squared. Right, and these are kind of our toolkit functions, right? These are ones that we had that list of our very general functions. So these are our very basic rational functions, but they can get more interesting. Like, for example, let's say minus 1, something like this. Okay, all right, and in which case we're going to be looking for, right, again, determining domain, right, and behavior, local behavior, and again, we'll develop the vocabulary as we get into this section. What's going to pop up from the graphs here is that they won't be nice and smooth, and well, they'll be smooth, but only when within the confines that are defined, right? So it won't be continuous, right? Some examples of what a possible graph like this might look like of a rational function would be something like this. Okay, and notice here, right, differences, there's kind of breaks in the graph from our polynomials, right, and we'll get into, these are called asymptotes. And we'll get into a formal definition of what we will call an asymptote, and sometimes, right, we have these kind of holes in graphs. All right, and we'll develop, how do I know I have a hole, a technique to determine is it a hole or is it an asymptote? right? Things like this, right? With the final goal being, or one of the goals of being, how do I graph something like this? Okay, all right. So, thank you.